Betelgeuse is a massive red supergiant star in the constellation Orion. It has captivated astronomers and the public alike for a long time. Its stupendous size is challenging to comprehend. If situated where our Sun is, Betelgeuse would extend beyond Jupiter's orbit, dominating the inner solar system with its sheer enormity. Perched on Orion's shoulder, Betelgeuse has become not only a symbol of the vastness of the cosmos, but also a subject of extensive scientific investigation because of its distinctive features. Unlike most stars, Betelgeuse shows significant unpredictability, accompanied by fluctuations in brightness that have sparked speculation about its potential to explode as a supernova. These fluctuations have been particularly pronounced in recent years, capturing both public and scientific attention. The James Webb Space Telescope has recorded a remarkable increase of 250% in Betelgeuse's luminosity, a change highly uncharacteristic of a red supergiant, indicating deep-seated processes within the star. Updates from social media have also documented an increase of 140%, with subsequent observations showing additional spikes in brightness, emphasizing that Betelgeuse is now one of the most closely observed stars in the night sky. As a result of these events, Betelgeuse has evolved into the seventh brightest star visible from Earth, consolidating its position as an extraordinary object of astronomical interest. The likelihood of Betelgeuse exploding offers astronomers a rare chance to learn about the life cycle of massive stars in great detail. Betelgeuse is categorized as a semi-regular variable star, meaning it undergoes periodic changes in brightness, changes illustrative of internal processes that observers otherwise cannot see. Since 2019, the star has exhibited increasingly erratic behavior, including the expulsion of a significant portion of its outer atmosphere in an event commonly known as the Great Dimming. This phenomenon caused unprecedented changes in brightness as well as radial velocity, leading to speculation about the star's impending demise. Despite these dramatic signs, predicting exactly when Betelgeuse might explode is extraordinarily difficult. Stellar evolution is inherently complex, and the sequence of events leading to a supernova depends on numerous internal factors, most of which cannot be observed directly. Currently, fusion is still taking place in Betelgeuse's core, burning elements such as helium, carbon, oxygen, and silicon. This progression will eventually lead to the fusion of iron, at which point energy production will cease. The core will no longer support the star's enormous weight, leading to collapse and, ultimately, a supernova explosion that could leave behind either a neutron star or a black hole. Historical observations suggest that Betelgeuse has undergone gradual transformations over millennia, but its current instability is notable. It might still be decades away from its final stages of life. Even so, its present behavior provides a unique window into the very end of stellar evolution, allowing researchers to observe processes usually inferred rather than directly seen. The incorporation of heavier elements into the core, progressing through oxygen, carbon, and magnesium, signifies a shift toward eventual collapse. Depending on how quickly these processes advance, Betelgeuse might explode within decades, or it might remain in this transitional state for thousands of years. This unpredictability underscores the complexity of stellar evolution, reminding scientists that even the most sophisticated models must account for a wide range of possible outcomes. If Betelgeuse were to explode within our lifetimes, it would be an unprecedented spectacle. The first signs of the explosion would likely be a surge of high-energy neutrinos and photons, signaling the release of immense energy from the core. Within days, the star would brighten dramatically, potentially rivaling the full moon and casting shadows at night. Over the following weeks, its brilliance could dominate the sky, with after effects lingering for months, offering an extraordinary opportunity to study supernova physics in unparalleled detail. Even if Betelgeuse does not explode imminently, its current fluctuations in brightness and oscillation patterns remain captivating. Observations of these changes provide critical insights into the behavior of massive stars and the processes governing their lifetimes. Each new measurement refines stellar models, revealing mechanisms that drive instability and mass loss in red supergiants. Events such as the Great Dimming, where Betelgeuse expelled outer layers, enable researchers to investigate how massive stars shed material and prepare for eventual disintegration. This process is essential not only for understanding stellar evolution, but also for appreciating how supernovae enrich the cosmos. Such explosions play a crucial role in the cosmic ecosystem, dispersing heavy elements across space and seeding the formation of new stars, planets, and ultimately the building blocks of life. Thus, Betelgeuse is not only an intriguing subject of study, but also a key player in the broader narrative of cosmic evolution, illustrating how the death of one star contributes to the birth of new systems throughout the universe. Advances in astronomical technology, such as the James Webb Space Telescope, have significantly improved our ability to monitor Betelgeuse's brightness in real time, providing data previously inaccessible. These observations reveal its often unpredictable behavior, including shifts in luminosity and spectral characteristics that challenge conventional models. By studying these changes, scientists gain insight into the mechanisms of mass loss, the dynamics of stellar cores, and the stages leading up to core collapse. These findings are not limited to Betelgeuse alone. They inform our understanding of other red supergiants and massive stars nearing the ends of their lives. Ultimately, the anticipation of Betelgeuse's supernova has captured the imagination of both scientists and the public. Unlike most cosmic phenomena, a supernova of this magnitude would be visible to the naked eye, possibly even during the day, dominating the night sky for weeks. Beyond the spectacle, it would provide a once-in-a-lifetime scientific opportunity to deepen our understanding of stellar death and cosmic rebirth. Astronomers research the physics of core collapse directly by observing neutrinos and high-energy photons that come from the core of a star. Debris and an expanding shockwave cloud would offer a comprehensive laboratory for studying interactions between stellar material and the surrounding space. While Betelgeuse is a close second, at about 600 light-years away, its distance ensures that any explosion poses no threat to Earth. Instead, it allows us to witness the event safely. Interestingly, observing Betelgeuse is like looking back in time. The light we now see left the star more than 6 millennia ago. Any catastrophic event that occurred since then may only now be moving in our direction. It is conceivable, though unlikely, that Betelgeuse has already exploded and we are simply waiting for that light to appear. This temporal delay is humbling, a reminder of the vast time spans and distances that shape the universe. Past unexpected events, such as the 1987 supernova that marked the explosion of a massive blue star, demonstrate the unpredictable aspects of stellar evolution. These rare occurrences have historically challenged existing theories and underscored the importance of constant observation. Similarly, Betelgeuse's recent erratic behavior offers an unmatched opportunity to refine our understanding of the final life cycles of massive stars. By examining its rapid oscillations, erratic brightness, and mass loss events, astronomers can better model the processes leading to core collapse and, ultimately, a supernova. Each new observation deepens our comprehension of how massive stars live and die, revealing the extraordinary forces operating within them. Betelgeuse exemplifies the balance between stellar fragility and resilience, offering insight into the complex interplay of nuclear fusion, gravity, and the processes that define the evolution of red supergiants. The enormous dimming event of 2019 marked a pivotal moment in Betelgeuse research. The star expelled a significant portion of its outer layers, causing unprecedented changes in its spectral and luminosity properties. These adjustments provided a rare chance to examine how massive stars shed mass, an essential step in preparing for eventual collapse. Understanding these processes has profound implications for astronomy, including how supernovae enrich the interstellar medium with heavy elements essential for the formation of life and planets. Each phase in Betelgeuse's development contributes to the cosmic cycle, demonstrating the deep connections between stars and the universe they inhabit. Observing the star as it nears the end of its life allows scientists to capture a precise snapshot of a red supergiant on the brink of collapse, providing lessons that extend far beyond a single stellar object. Modern astronomical instruments now enable real-time observation of Betelgeuse's fluctuations, a feat once impossible due to technological limitations. These observations have revealed highly complex behavior, including irregular cycles of brightness that deviate from historical patterns. Such data are invaluable for refining theoretical models and offering empirical evidence to predict the behavior of stars across different masses and evolutionary stages. By monitoring Betelgeuse, astronomers can examine the life cycles of massive stars in unprecedented detail, enhancing our understanding of the processes that shape galaxies and the cosmos as a whole. Its erratic luminosity, spectral shifts, and mass ejections provide a comprehensive case study of stellar mechanics, from core fusion to the dispersal of matter into space during a supernova. Betelgeuse's final outcome, a supernova, will provide an extraordinary opportunity to study one of the universe's most energetic events directly. When the core collapses, the ensuing explosion will release neutrinos and high-energy photons detectable on Earth, offering insight into the internal processes of the star. The expanding shockwave and ejected material will illuminate surrounding space, creating an unparalleled laboratory for observing the physics of a supernova. Although the timing of such an event remains uncertain, its potential would reshape our understanding of massive stars and highlight the importance of continuous monitoring. Each fluctuation in Betelgeuse's brightness adds a piece to the puzzle, revealing the complex dynamics of gravity, nuclear fusion, and energy transfer that define the life and death of enormous stars. The study of Betelgeuse also emphasizes the role of massive stars in the cosmic recycling process. Supernovae disperse elements such as oxygen, carbon, and heavier metals into the interstellar medium, enriching it for the creation of new stars and planetary systems. In its final stages, Betelgeuse illustrates this process directly, serving as a contributor to the ecosystem of space. Its instability and eventual demise are not isolated events, but part of the broader narrative of stellar evolution, chemical enrichment, and the formation of life-supporting environments. Each observation thus advances both the fundamentals of astronomy and our growing understanding of how the universe works. Even without a supernova, Betelgeuse continues to provide an abundance of information. Its current erratic behavior, rapid oscillations, and changing luminosity serve as a natural laboratory for studying massive stars. By tracking these changes, astronomers can test and refine their models, bringing us closer to understanding the ultimate fate of one of the night sky's most iconic stars.